A very good afternoon to all of you. It is my great pleasure to introduce today's esteemed speaker, Professor Tanuka Chattyopadhyay. Professor Tanuka Chattyopadhyay is currently serving as a professor in the Department of Applied Mathematics, University of Calcutta. She has completed her BSc in Mathematics, MSc in Applied Mathematics, and PhD degree from University of Calcutta. She is the recipient of many prestigious awards and individual member of International Astronomical Union or IAU since 2018. Professor Chattyopadhyay has around 50 peer-reviewed publications in high-impact factor journals along with 4 books. With the wealth of her expertise, Professor Chattyopadhyay is here to enlighten us with insights that promise to expand our understanding of the technical landscape. Without any further delay, let's extend a warm welcome to Professor Tanuka Chattyopadhyay. Ma'am, please.
Hello. So, distinguished guests and professors and my beloved students, I am very much thankful to Professor Guo, Dean of Technology, and Professor Pal, Professor of the Department of Radiophysics and Electronics and University of Calcutta for giving me this fabulous opportunity to tell something about database analysis for the astronomical data. And also an additional opportunity that it gives me pleasure to meet some of my old friends and professors after a long time, after COVID period. So, about Professor N.K. Dasgupta, I can say he used to come to our department and with my supervisor, Professor Meghnad Basu, they have a long discussion, and that discussion was very enchanting in the sense of academic matters, and I have learned many things from their discussion. So in a sense, I am very much indebted to Professor Dasgupta for teaching me astronomy and astrophysics in an indirect way. So, after the launching and the success of Chandrayaan-3, we are very much inspired. We are having images of the surface of the moon by rovers, but we are not only satisfied with the images only, but we like to study the various properties of the moons. So those are some topography, the variation of the magnetic field, the thermal conductivity, the temperature, many things. So what are the galaxies, also we collect data from various virtual archives which are free of cost. For example, Sloan Digital Sky Survey is a virtual database of galaxy characteristics like spectroscopic, morphological, then photometric properties, and we can collect those data from Sloan Digital Sky Survey free of cost, and we can do research analysis, the database. In these days, the database analysis, the artificial intelligence, the data in various multi-wavelengths are very much demanding, and we have to gather significant information from this data. So I thought, why shouldn't I discuss about the different aspects of data analysis? Because for galaxies, once you can do the data analysis, you can do the same things, you can apply the methods for other systems, astronomical bodies and other systems also. So I have chosen my topic as clustering and classification of galaxies, a multivariate database approach. Now, what is a galaxy? Galaxy is a large ensemble of stars and stellar remnants, an interstellar medium of gas and dust and dark matter, that is the matter we cannot see. But how it is felt? It is felt through its gravitational existence, and the whole system is gravitationally bound. Now, there are primarily three types of galaxies: spiral, elliptical and irregular. From the pictures you can see the spiral has a spiral arms around a solid body which is called the nuclear bulge, and at the center of it there is nucleus where violent activities are taking. So there are signatures of shock waves from the central part of the galaxies, and it is thought there is a supermassive black hole staying at the center of spiral galaxy. Now, elliptical galaxies. These are of elliptical shape, and these are very old type of galaxies, and some galaxies they don't have any shape. They are called the irregular galaxies. But in spite of this, there are many galaxies like dwarf galaxies, ring galaxies, starburst galaxies. And some interacting galaxies. This is the picture of our galaxy. Our galaxy is a spiral galaxy. This is the edge on view. That is, our line of sight is along the direction of the galaxy. So it is the edge on view, and the right side it is the face on view. That is, our line of sight is perpendicular to the galaxy. So this is a spiral galaxy. Our galaxy is a spiral galaxy, and it is a two-armed spiral galaxy. Along the spiral arms there are gases and stars. From the gases, stars are formed, and at the center there is nuclear bulge, and there is a solid body. It is called the nucleus, where some violent activities are going on, as I told you about. Now, this is the Hubble's tuning fork diagram due to Edwin P. Hubble. He observed many galaxies and he classified the galaxies. You see, along the tail there are elliptical galaxies, and the two arms are spiral of different evolutionary stages and part spiral. So if there is a bar at the center of the galaxy, it is called bar spiral galaxy. But you see that this diagram is not scientific classification. It is only the morphological classification. And we know nowadays the ellipticals are older than the spiral galaxy. So this classification is not very scientific. Why the study of galaxies are so important? Because they are the building blocks. They are the link between large scale to small scale structure like sun and solar system, and the galaxies are very luminous because we can see galaxies from large distance. At very large redshift we can see galaxies looking into space and looking back in time. That is, more distance means more looking back in time. Galaxies we see today are endpoints of ultimate evolution which started in the early universe immediately after the Big Bang. So if we can study the galaxies, we can study the evolution of the universe and origin of the universe, how the universe was born, that we may have some glimpses from the study of the galaxies. Now, what are the existing theories of galaxy formation? There is no unique theories because the galaxies are huge in numbers. So there are many theories and many pros and cons about that. For example, one theory is the monolithic collapse model. So according to this model, a galaxy is formed by the gravitational collapse of a large big cloud, and the color distribution here, which is due to the metallicity present in the galaxies, is unimodal. Then there is another theory, major-marcher model. Here a galaxy is formed by the merger of two spiral galaxies. And we know in spiral galaxies, the halos, the metal core elements are there, in the disk, the metal rich elements are there. So the color distribution is bimodal. Then multiphase dissipational model. That is, the galaxy is formed by the merger of two spiral galaxies, and the gases in the spiral galaxies, they give rise to more stars which are metal rich. So there are multi-phase dissipational model, that is, gas is involved there. Then dissipationless merger model, or we can say tri-merger, where the galaxies are formed by the merger of two disk galaxies which are have no gas in their disk. Then accretion and in situ hierarchical merging model, where the galaxies are formed by the satellite merging of the satellite galaxies in their locality, and then they form a big galaxy. But all these theories, they are not very unique, and all the theories have their pros and cons. So no unique theory of galaxy formation is still found. Then there are rotation. Rotation, we can say there are different type of rotation. For example, solid body rotation, where the angular velocity is constant. So V is proportional to R. Then there is Keplerian rotation. V square equal to Gm by R, where n is constant. For example, our planetary system. Then differential rotation, the rotation period of a body varies with latitude and it occurs in gaseous body. Then galactic rotation. Here the velocity is constant. And as you see the rotation curves, which is actually the plotting of a rotational velocity with the projected distance, it gives you that first part, it is very solid body rotation, and in the second part it is Keplerian, and in the third part the velocity is constant. So from this rotation curve we can have some idea what is the composition of the galaxy. The nucleus is a solid, gives rise to solid body rotation, and then the galactic bulge gives you the Keplerian rotation, and then in the outer part rotation becomes constant. So when V equal to constant, n is proportional to R. So this is the signature of the dark matter, that is, mass is proportional to R. Mass increases with the distance, but we cannot see that mass because it is dark. It do not emit any light. But how do we understand their existence? We can understand their existence from their gravitational existence. From virial theorem, we know that there is mass. So this is called the galactic halo. Then there are some scaling relations in galaxies. There are actually some regression lines and regression planes. For example, Faber-Jackson relation. This is a relation between the luminosity and the central velocity dispersion. So it is a regression line. So it gives some information of the galaxies. Then there is another scaling relation, which is a regression line, Cormenti relation. Correlation between the luminosity and the effective radius of the galaxy. Effective radius means the radius in which almost 50% of the mass of galaxy is embedded. And there is another regression plane which is very significant. It is called the fundamental plane. It is a regression plane between the effective radius, central velocity dispersion sigma, effective intensity IE, or the effective surface brightness mu E. These are the similar things. So we see it is a plane, and some points are seen on the figure. We see these points are the different galaxies, and we see that there are some scatters. I mean, they are somewhat away from the regression plane. Now, what are the physical basis for the fundamental plane? So, if we go through the fundamental plane, we see that it is log Re equal to 2 log sigma plus 0.4 mu E plus constant, which is close to the fundamental plane, and it is the virial plane, and then the fundamental plane is log Re equal to 1.4 log sigma. So it is the close to the virial plane. Now what is a virial plane? Virial plane is a plane which shows that the astronomical bodies are in dynamical equilibrium. So since fundamental plane is close to the virial plane, we can say fundamental plane shows the signature of the degree of the dynamical evolution of the galaxy. So if the scatter is small, then they are close to the dynamical equilibrium, and if the scatter is large, so we can see from the figure just I showed previously that they are much away from that, and by point for the galaxies we can see how much they are far from the dynamical equilibrium. So the fundamental plane is very important plane in that sense. Now there are some scaling relations among the globular clusters, that is one kind of star clusters whose age is comparable to the age of the galaxies, provided the mass to light ratio is constant. So both the relations are close to virial theorem for constant mass to light ratio, which is the signature of dynamical evolution, that is less scatter of points from virial. Now we get different types of data from the galaxies. So those data are spectroscopic data, then morphological parameters, then photometric data. So what to do with that kind of data? So to get important, significant information using those data, that is very important. So that we do by methods which are very scientific rather than the 2-point correlation diagram which often physicists used for their study, because they are not acquainted with the present statistical multivariate setup, which is more objective and more scientific for classification of data. So there are several ways under statistical analysis. Now the one point is that there are many parameters. For a galaxy, there are, say, we can have from the different virtual archives some hundreds of parameters. Now if we do some statistical analysis in that multivariate setup, it becomes very complicated. So what is our motto will be? We have to apply any such methods where we can reduce those number of parameters and which defines the maximum variation. So to reduce the huge number of parameters to smaller numbers, giving the maximum variation of the data. So different methods are used for that, and these methods are called the dimension reduction technique. So for data analysis, dimension reduction technique is very important. Now there are two types of data. One is the Gaussian data, which follows the normal distribution, the multivariate setup, and non-Gaussian data. When the data is Gaussian, we apply the principal component analysis. What is principal component analysis? Actually, in principal component analysis, the principal components are the linear combinations of the various parameters. Now, but in principal components, we can see that 2-3 components giving the maximum variation, for example, say 96% threshold like that. So actually those large number of parameters are reduced to 2 or 3 principal components, and we can work with those principal components which give you the very clear picture of the properties of the galaxies in the scenario. But when the data is, so what we do in the principal component? In the principal component, physically, what we do, we start with a variance covariance matrix. Since it is a real symmetric matrix, so we can diagonalize, and the diagonal elements are the eigenvalues, and the eigenvalues follows a chronology. That is, the first diagonal has the maximum variance, the second one less, third one lesser, like this. So when the variation reaches up to that threshold value, for example 90%, in some of our analysis we have done that, when it is a 90% variation, then we take those principal components, and the values of lambda in that case is approximately equal to 1. So in that way, we use principal components instead of a large number of parameters, and we say it is a dimension reduction technique for Gaussian data. Now for non-Gaussian data, what we do? For non-Gaussian data, actually we separate the noise from signal. So what we do, and just skip these things because the algorithm I have physically already described. For non-Gaussian data, these things I will describe later. So X is the data in our hand, and A and S. S is the signal matrix, and A is the mixing matrix. So from this relation we find S, the signal, which is X A inverse. So in this way we get the signal only and reduce the noise, and we get the IC component, that is the independent components, which are the linear combinations like the previous principal component analysis. But the difference is that the principal components are uncorrelated, but the IC components are also independent in a sense. So with these independent components, we physically interpret all the parameters, and then we do the analysis for the given data. Now I am coming, what next we have to do? Now once I get the principal components or the independent components, what we do? Now we have components instead of parameters. Now we have principal components or independent components in our hand without parameters, but these components actually explain some physical characteristics of the galaxy. Now we do a cluster analysis, which is a tool for exploratory data analysis, and By this cluster analysis, we take the principal components or the IC components as the parameters, and we do and classify the objects in homogeneous groups. So what we do? We do cluster analysis is one such method which is the art of finding coherent subgroups in a collection of objects through which their properties can be studied in a more scientific way. So there is a special algorithm given by McQueen, which is, what is that? Given K, that is, you define that there are K number of homogeneous groups. Then you partition the items on the ad hoc basis, and you calculate the center of mass of those groups. Now you compute the distance. Here distance means not the physical distance but the multivariate parametric distance. So from one point to another point, and for how many parameters you have taken, you calculate the distance. Mainly it is Eulerian distance. Decalculate the centroids for the cluster. Suppose you compute the physical distance, not the actual distance, depending on the parameters, and you see that you have put one point in a group which is further, but another point in another group which is closer. Then you take that point in the one group and you take this point which is the further one to the other group. So in this way the simulation goes on, and ultimately there is a convergence that you get the coherent groups. Now you study the different properties of the groups. Now you can use the two-point relation to find the physical interpretation. And to find the optimum number, we just use 1 by p, where p is the number of parameters, expression of xk minus ck. Ck is the centroid of the kth cluster, and then we calculate the distortion, for which for the distortion, from the distortion we calculate the jump jk, which is equal to tk to the power minus y, and y equal to p by 2, where p is the number of parameters. The optimum number of cluster is valued k associated. So in this way we computed the optimum number groups for PCA analysis. But in ICA the variation is not very precise. It is not that the variation will be the first 4 components, because in IC such lambda things are not there. So another mathematics is there. So what we do in IC we do all the permutations and take the physically interpretable number of groups. So in this way we just decide the optimum number. Now I am just giving you how the data analysis is done for 2 case studies. One is the multivariate study of the star formation rate in galaxies by modality revisited. They are my collaborators. Now the data set is a value added galaxy catalog. What is a value added galaxy catalog? Value added galaxy catalog. Suppose you take some data set from some archive with a number of parameters, but you need more parameters. Then you take the data set from another archive with another type of parameters. Now you just combine, that is, you add those 2 data sets through another archive known as the Aladdin. Here now, as a result, you get so many parameters of the galaxies. In this way, the value added galaxy catalog is developed from different virtual archives, and we have done also that value added galaxy catalog from different archives. And the data we have used in this study are photometry, spectroscopy, morphology, chemical composition and kinematics of the galaxies. Star formation rates and specific star formation rates, they are not observable parameters but computed parameters, but we have not used in our analysis for these parameters, But after the analysis, once we found the coherent groups, then we use these parameters as a regression relationship. So these are the different ionized lines, then equivalent fields, then leak indices. These are the absorption lines in the spectral feature of the galaxy. Then D4000N. This is one parameter. Actually, galaxies have stars. So when there are many stars, there are heavy stars. What happens? In heavy metals, there are many electrons which absorb the light coming from the galaxy. So there is a lag in the continuum. This is called the Lyman 4000 angstrom, and it occurs at 4000 angstrom. It is called Lyman 4000. But in Stardust galaxies, there are ionized lines. So these metallic lines are not found. So the width of the D4000 actually reduces. So when there is a small width, it indicates the galaxy is younger, and when there is a large width of the D4000, then it indicates it is older. So D4000 is very important parameter for galaxies. So similarly, we have different other parameters also. And the methods we have used here, independent component analysis first, because it is a non-Gaussian data set. Because we have tested for multivariate Gaussianity Shapiro-Bell test, and it is a non-Gaussian type. Then with the independent components, we have taken all the combinations of the independent components, and we have chosen from that the significant independent components, which are very small in number compared to the number of parameters. Then we have done K-means cluster analysis, which I have told you about, and we have found the optimum number of groups. Then we have predicted a star formation rate in number of parameters through a regression analysis, which is a very different type, stepwise regression analysis. Because in stepwise regression analysis, it selects all the parameters, but ultimately detects those parameters which are very significant. So this is different from the original regression. So with this, we have just found 9 IC components are very important, and their physical interpretation is velocity dispersion, then ionization, then metallicity, then surface brightness, then structural parameters. Then we have studied the properties of the groups, the density. Actually, we have bimodality, one young and one old type of galaxy, but we see that the different groups have different density in the middle also. There is a green valley also there. And also we have compute H delta. H delta is the Balmer lines, and versus D4000A. You see from the diagram, when the H delta is large, D4000 is small, width is small. That means they are young galaxies. And in some galaxies, when the D4000 is large, then H delta is small. So they are older galaxies. So in this way, we study the different physical properties of the galaxy. So another diagrams we have used, which is very physically important, Baldwin-Phillips and Telrovich diagram. These are the cuts of different absorption line ratios, and on the left hand side it shows the starburst galaxy, right hand top it shows the radio galaxies, and right hand down it shows the liners. But this galaxy classification is not so simple. So you see that in different groups they have different interpretations. And also we have computed one concentration index. When C concentration index is SAR6 R90R, so this is a distance where 90% of the light is confined, divided by the R50, that is 50% light is confined. And this is called the concentration index. When C is less than 2.6, then with 2 peaks we get C equal to 2.5 and 7.5. So these also have some physical interpretations, that is whether they are young or old. So various conclusions we have done from these physical interpretations of the various coherent groups. Now for the second case of studies, we have done the investigation of the effect of bars on the properties of spiral galaxies, a multivariate statistical study. They are my collaborators. The motivation is that subjective classification of spiral galaxies is not sufficient study. Here we have done the classification of only spiral galaxies. Spiral galaxies are various types. Bar spiral. When there is a bar, they are called the bar spiral. When there is no bar, they are called unbarred spiral, like this. So what is the motivation behind that? Subjective classification of spiral galaxies is not sufficient for studying the effect of bars. Then multivariate tools are the best ones. In this work, we have also used a VAGC catalog, that is the Value Added Galaxy Catalog from SDSS DR7 Virtual Archive. Initially, the dimensional reduction through independent component is performed, and we have 48 independent components which are very significant from the study. Subsequently, we have done the K-means cluster analysis. I have already demonstrated all the methods for it. So what is the novelties? In this study, we have prepared a large data set of spiral galaxies from DR15 and cross-matched with its corresponding bar properties, because the bar properties are kept in a separate virtual archive. So we have to match those, and that bar properties are given in Galaxy Zoo. The work contains several novelties: a large data set, large number of observable features, large number of estimated features, application of ICA because the data set is non-Gaussian. The justification of ICA to the fact that the present data set is non-Gaussian. And also we have done some model-based clustering, Gaussian mixture modeling method for testing the robustness. When we take any data set and find some groups, that is not sufficient. We always do the same analysis by some other methods, and if we see that we get the same number of groups with the same properties and same compatibility is there, then we can say we become very confident and we say yes, our data analysis is correct because it is giving the same results from the different methods. So this is called the robustness. So robustness we have done by Gaussian mixture modeling. It is a model-based method, and the method I see, it is not the model-based. It's exploratory. I mean, the cluster analysis is exploratory type of method. So the data set here, the several link indices. These are the absorption features. Then there are equivalent weights, absorption, then spectroscopy, and these are the different types of spiral galaxies. We have used this is a sample representation, and we have used these galaxies in our data set: barred, weak barred, and unbarred galaxies. And we have studies. This is the Gaussianity before the analysis we have done, and the methods we have used ICA. Optimum number of ICs is 14, and their physical interpretations are metallicity, then the absorption feature, then the color, then the velocity dispersion, the metallicity, and high level ionization. And here we also drawn the PPT diagram, and we have gained information about the different groups, and also we have done some 2-point correlations. Once we have found the coherence groups, metallicity versus login, several things we have done. It's a big analysis, And the conclusion is the entire data set reduces to 12 significant ICs, of which 5 ICs are physically significant. Their metallicity, gamma absorption, color, velocity and metallicity. And the cluster analysis gives us the 12 groups which have several different properties, and these are the conclusions. And the main conclusion is that this is the very new feature reflected in the present study and concludes that bar formation is not always one-way phenomenon but may get dissolved in course of time in oldest and medium age range galaxies. So this is all about to say that how data analysis, because all are very much excited about the data coming from the Chandrayaan 3 and possibly from L1, Aditya L1. So what to do about that data is very important for us. That we have to learn how to do the data analysis scientifically in the age of artificial intelligence and multivariate studies. So I thought this lecture will be helpful for the new generation of students. Thank you.
Thank you, madam, for your talk, which was a kind of fallout of some discussion that I had about highlighting what kind of work in this or related domain is being done in the university itself. Because we had two very enriching talks by experts from Tanuka as well as from Aries. But where do the university, our university, stand in terms of any kind of work related to astronomy and astrophysics? That was one of the major motivation in this particular seminar or lecture. So now if there are any quick questions, Madam could answer that.
Okay, thank you. Is it on? Okay. Thank you for your talk. I have a very nice question. You discussed PCA and IC techniques. Basically, you wanted to reduce the number of parameters in this microanalysis. Both the techniques have its advantages. And my question is that how to decide which type of analysis we adapt and how to validate that this PCA or IC is better.
As I have told that for spherical data and Gaussian type data, we generally apply PCA. And PCA is very predefined method. Here the variations are easily explained, that is the eigenvalues. So as long as the eigenvalues are equal to 1 and the variation is some threshold say that should be decided by the researchers, we have decided 90% variation. Then we have chosen those PC components. But in case of IC, since the optimum number of such components is, there is no such predefined theory. So what we have to do, we have to take in all the combinations. All the combinations of these ICs and see which components gives you, because it is a physics, it is not only a mathematics or statistics, it is physics. Unless or otherwise the physical interpretation is not good, we cannot apply just for mathematically computed things for our study. So we should check, we should take all the possible combinations.
But that should have physical.
Yeah, which are physically interpretable, we should take those components. Yeah, because the expert should have the knowledge also. Because who is astrophysicist, only he or she can understand. Who is the expert of moon, he can understand. So in that case, the experts will tell us that whether these components are physically more interpretable than the other ones. So in case of ICs, we have to do that. And in astronomy, most of the data set are non-Gaussian. So generally, we have to apply IC because the spherical data is very rare in astronomy.
Now these actually principal component analysis, they are
actually principal components is valid for when we started our research, we actually did PCA, but later when we came to know about, because the statistics is developing day by day, new methods are coming in the field. So we have to keep pace with this method and see what type of methods now we can apply, which we cannot apply, but applied in the past, but now we cannot apply. So we have to also keep pace with the latest developments of statistics as well as mathematics for mathematical modeling also.
Yes. Statistical tools alone is not enough.
Yeah.
It's not enough.
That's why I am telling it is a multidisciplinary work. All the scientists from the field of mathematics, statistics, physics, astrophysics, they should combine. And in a sense, in these days, why the multidisciplinary research is supported and they are encouraged. So this is the reason for that.
And also, this is an image data, right? Image data. This data is an image data.
Data, actually there are images, because in a what we have done the image processing also. Because in a recent part, we have done some image processing. We have simulated, actually the stars, they do belong to a certain diagram, which is known as Hertzsprung-Russell diagram, which shows the evolutionary phases of the stars. Now, in the star clusters, globular clusters, we have drawn the simulated HR diagram, and we have image processed with this observed HR diagram. That also we have done. Yeah, that is the two-dimensional histogram matching. Yeah. That we have done in one paper also. Recently, that has been published in MG. Yeah, that also can be done. And for the image processing, you can use different type of distances and see the compatibility. And also, you can use the model-based clustering also. For example, Bayesian type.
Thank you, madam. So if there are no further questions, may I request Professor Shankar to kindly offer our token of appreciation, Professor Tanuka Chattyopadhyay. So now we have come to the last leg of the program, where I request Dr.